Yeah, that was a good one. Okay. First order of business. Quiz coming up Thursday. We're going to cover today just 26 and 27. Should take like 10 minutes maybe. Then 28 through the end is skip. It's all review. So if you want to do them for extra credit, sure. I'll give you some extra credit if so if you got if your problem set average is a little low and that's bringing your grade down, you could, these are all fairly easy questions. You just use, like 28 is just use spring energy. So you throw in a 1/2 kx squared. 29 is just conservation of energy. 30 is also conservation of energy. You're just going to do it, you do an MGH. At every point, the MGH plus the kinetic energy is conserved. So you just do that. 31 and 32, you might have to dig into the old mind palace of your notes to do we've done those problems for a frictionless block, so then we do the same thing for a rolling object. And then 33 would be write a full summary of, for example, F equals MA turned into tau equals I alpha, and 1/2 MV squared turned into 1/2 I omega squared. Anyway. If you want to do them for extra credit, great. You don't have to though. So just to this one last clarification, 28 through 33, skip those. Oakley dokley. All right, 26 is, I think it's an interesting question. It's not super simple though. So 26 says, suppose you had these 3 objects, same radius, same mass. Okay, this one is is solid disk. This one is a solid sphere. Okay, and this one is a ring or a hollow cell. And they're all going to have, say you exert some torque on them, with a force. All right, first order of business would be, if they all have the same force exerted on them over the same radius for the same amount of time, who do you think would end up spinning the fastest?
It's the
solid sphere.
Smallest I value.
Good. That's the important thing. Not that you have the I values memorized, is that you understand that the smallest I value one is going to be the most willing to spin, right? He's going to respond. So there's a bunch of ways you can look at this. I'm going to write a few formulas that would inform you on this. So like first one might be, well, what is torque? Torque equals a force times a radius. So the first thing you would look at, that's the definition of torque, right?
Yeah.
So all of these guys are experiencing the same torque, right? Okay, and then torque equals I alpha. So if they're all experiencing the same torque, okay, and
Teachers, please excuse the interruption. At this time, could we have the Academic World Quest Club please come to the main foyer for your photo? Once again, those in Academic World Quest, please come to the main foyer. Those students that are in Spotlight Club, Drama Club,
is it photo day?
your photo today will be during 4th period. We'll make an announcement.
By Julia. Peace
Once
out.
again, if you're in the Drama Club, please do not come down at this time. We will call you out during 4th period. Thank you.
Okay. So anyway, if they all have the same torque, and you want to know how their acceleration is going to look, well, does that make sense that the bigger your I value, the smaller your alpha, the smaller your acceleration? So the answer to part A would be the solid sphere. Solid sphere. It says explain, so an explanation doesn't have to be a novel, just a quick explanation. Throwing an equation in an explanation is a really good way to support your answer. So something like, well, They're all experiencing the same torque, so the smallest I value would experience the greatest acceleration. Of course, the time thing is, I mean, it might be good to throw the time in, but it's all the same time as well. So I might rewrite this alpha, right, as the change in omega over time. And since it started at 0 omega, the change in omega is just omega, the final omega. So again, looking at this, if this is the same and this is the same, then the smaller this is, the bigger this will be at the end. Okay? So these guys all together kind of give us the answer to part A. Okay. Part B. Does anyone know, or does anyone have an educated guess at least of who would have the greatest angular momentum at the end of this? This one's a little tricky because you might go, well, the solid sphere is going to be going the fastest, but he has the smallest I value as well. And we know that L equals I omega, right? And by the way, this formula, if you multiply the T over here, you get another really famous formula, which is torque times time tells you the change. Did we break? Did the computer break? No, it's still working. That's weird. Does that make sense? Again, assuming it's starting at rest, I could say that the final angular momentum is equal to the change in angular momentum. Okay, so they all experience the same torque, right? And over the same period of time. So what's true about their momentum? Okay. Are there any questions? It's a bit. I mean, in physics, though, you really the whole, like if I drop a 5 kilogram block and a 10 kilogram block, which one hits the ground first? They hit at the same time. Like physics is full of questions where the answer really is the thing you're looking at is not going to change, or it's held constant. So it's a little tricky, but definitely, when you're doing physics, you want to keep an eye out for what kind of things would just stay the same here. So the idea there is, I don't care what these objects are really, if they're free to spin and you exert the same torque over the same time, they have to have the same angular momentum at the end. Doesn't matter what shape they are. Okay. C is the trickiest one. Who will have the greatest kinetic energy? And I'm just going to tell you the answer. This one's really, unless someone has think they have an answer to this one?
Would it be the hollow cylinder? No. Okay, no.
This one's tough because the answer is the solid sphere.
What?
And this one's weird because you go, well, it gets, okay, so let's get to the heart of the question, which is, well, okay, kinetic energy, right? The kinetic energy is 1/2 I omega squared. We discovered earlier that the SS, the solid sphere, is going to have the biggest omega, right? So, but he also has the smallest I. So how's that going to balance out? That's what makes it very not obvious what the answer is. So one argument is, and then we're going to kind of prove it in 27, is, well, we have this theorem. Remember this one, work equals force times distance? So the rotational version of that is that the change in energy for a rotational system is not a force, it's a torque, and it's not a linear displacement, it's an angular displacement. Does that make sense? Does that ring a bell? You guys remember doing that one?
Yes.
I think it's the first question on here, if I'm not mistaken. First or second. Yeah, it's part B of the first question on this problem set, because we derived this one. Cool beans? Okay. So what does that tell us? Well, it tells us that for all those shapes, they all have the same torque, right? They're all experiencing the same torque, but who's going to rotate the most? Who does the biggest rotation?
Well, you said it was the solid.
The solid sphere. Because we established earlier that the solid sphere has the biggest acceleration, right? So therefore, he's going to turn the most radians while he experiences that torque. Does that make sense?
Mhm.
You sure there's no questions? It's a pretty tricky thing to think about, I think. So same torque, but the guy with the smallest I value should turn the biggest number of radians. That's what that number is. So therefore, this value should be bigger for the solid sphere. Okay. Nope. If there's no questions, we'll move on. So then 27 is asking us to basically like, well, okay, that argument makes some sense, but can we prove it a bit more concretely? Can we derive a formula relating a torque exerted on an object to its final energy? So just read the question, read it carefully, make sure you understand what it's asking. I'll make another Shrek for you. Whatever. The point here is just, I make a weird object, and now I can just to emphasize the fact that this is just some object with an I value of I. Right? It may not even be expressible in terms of MR squared. It might have some strange formula. So anyway, there's the I value for this guy. And so what if we exert a torque on him? Okay, so a force would generate a torque. So I want my final formula to relate his I value, his inertia, to the torque exerted on him over some time interval t, and I want all of this to talk about the energy. So the question is, how does all of this combine to give us the energy? Does that make sense?
Mhm.
So what we might do is start off with, well, okay, if I want an equation for energy, let's write a formula for the energy. What's the energy of a spinny guy? One half I omega squared. If you're thinking, what about the plus 1/2 mv squared? Well, he's not moving, right? He's just spinning on an axle.
Oh,
So guys, on your quiz, well, at all times, but especially on your quiz, make sure you're being very careful distinguishing between, is this object rolling or is it just spinning on an axle? Okay, and I've tried my best to make the questions as clear as I can make them. And if you need clarification during the quiz, I'll tell you. Nothing is rolling. Okay, so anyway, that's the total energy. So then I might say, well, what letter do I not want to live in this equation? I don't want the omega. So over here, I'm going to figure out a way to substitute something else in for that. And so the trick is, you're going to go, well, how do I relate omega to like torque and time and I? Because those are the things I want to be in here, right? There's one we just looked at, a formula that involves angular momentum. Torque times time tells you the change. This is a really important one to know. This is one you got to know. Now wait a second. If the thing started at rest, which I think I wrote in there, yes, initially at rest. So if you started at rest, then this is just the final momentum. And what's momentum? Momentum is I omega, right?
Wait, Mr. Hall.
Yeah.
This might be like kind of a dumb question, but since we're starting at rest, won't you know like some of the values just being zero because there's no movement? Like you go like for initial.
Yeah, like omega naught is 0 and well, that's it actually. Well, L, well, okay, here's the thing. So the change in L, right,
Yeah.
would be the final L minus the initial L. And like you said, this is 0. So that's why I say that the change in L really is just the final L.
Okay.
And then I say, well, I know that L is equal to I omega. That's the definite. So that this is a really big one. I mean, you really want to make sure you understand this thing for the quiz, right? That's basically the definition of angular momentum. Okay. Are you guys still with me? Does this make sense?
Mm-hmm.
So therefore, and this is a result we've seen before, right? Is if you exert a torque over a time period on an object whose inertia, Lindsay, could you not read a novel, please? Thank you. If you exert a torque over a time on an object with a known inertia, then the final rotational speed would be this, okay? So then I can replace this right, with that. That make sense?
Yes.
Now engage the thinky winkies. Can we simplify this in our head? Maybe?
Yes. 1/2
1/2, so I'll put a 2 on bottom.
2i, then right because you have 2i on bottom, 1i on top.
We'll have an I squared on bottom
Yeah.
and an I on top, so one of those I's cancels out and I'm left with a single I on bottom.
And then parentheses.
Times t squared.
Well, yeah, you can write it as tau t squared or tau squared t squared. I kind of like tau squared t squared. This just helps me keep straight, I think, that if I double the torque, what do I do if I double the torque and keep everything else the same? What happens to the energy? Quadruple. So doubling the torque quadruples the energy. Doubling the time interval, this is kind of surprising, I think. If you double the time interval, it quadruples the energy. So you exert that torque for twice as much time, you get 4 times the energy. If you double the inertia, you got the energy in half. So what this tells us is that the small I value is going to correspond with a bigger E value. And is that what we said for the previous question? The solid sphere, the smallest I value, the solid sphere, had the biggest energy. So there you go. That proves it pretty conclusively. Okay. All right, we're skipping the rest of the questions. And so for all the Twitch fans, the practice quiz is on Google Classroom. You can take a look at that. Let me know if you have any questions.